Engineering 305, example problem 710. I'm going to do this one a little differently. I know you guys don't know this when you're watching this, but I got a little bit of a cold, so my attention span's a little bit smaller than normal. Imagine that. And so I'm going to show you how I would go through this. I'm going to show you some of the tricks that I'm going to employ. I'm going to try to follow their solution in the book fairly closely, but only fairly. And we'll get to answers, and we'll see how they relate, and then we'll make decisions about our processes and about what we want to do moving forward. So let's take a look at this problem. So example problem 710, a beam is simply supported and carries a concentrated load of 1,800 pounds at the center of a 15-foot span. I don't have that picture for you. I did not include that. I'll add that in a sec here. Actually, let's put that on the screen. There you go. A little bit of a pause later, and it's at the bottom of the screen. If the beam has a T cross-section, which is shown, and that's what I have the picture on the side, that T, which is laminated, or it's a wood beam, determine the average shearing stress on a horizontal plane 4 inches above the bottom of the beam and 6 feet from the left support. All right, that is a lot of information right there. So first thing we're going to do is, one, we've got to calculate what, didn't want to change colors there. We've got to calculate, let's say that's 6 feet. We've got to calculate what the load is, what that shearing stress is, because our equation is always going to be of the form the shear stress is equal to. Now the big equation that we don't want to work with is minus VQ over IT. What I'd much rather work with is the equation for beams, which looks like that. The average stress is VR over the area of the web. So that would be much better, area of the web. But either way, I need to know what V is, and I need to know what A is. I'm going to wind up calculating Q. I might as well get started on all this stuff. Well, the first thing I'm going to tell you, because we've got to just do this in chunks. So for part A, first I have to find VR, and that means I've got to find all the reaction forces, and I've got to do the whole free body diagram. I need to find I need to find Q. Do I need to find T? Yeah, I do. I need to find the thickness too. Well, I know what the thickness is. The thickness is, it's a 2-inch wide beam, so I'll just write that down. The thickness is equal to 2 inches. All right, let's start pounding through this. So the first thing I wanted to attack was I. And why would you say that? Why would I do that? Well, let's get rid of this. And I went to SolidWorks because that's what I've been trying to teach. We have tools for this. And so I drew it with the coordinate system is right there, like that. And I got to look carefully at my results. So I got to sit up a little bit. It can't be quite as reclined. You can see this label here. That's where the centroid is, and this is my YY axis. And so I can look, and IYY is 533. And now maybe that's a little small on the screen. Trust me on that. IYY equals 533. And then the other thing it's telling me is where the centroid is relative to the coordinate system. Since I know my coordinate system is here, you can see my x is equal to 1. Oh, you can't see that because the figure's in the way. X is equal to 1, and y is equal to 8. So that means I go this way 1. Well, that makes sense. I split that beam up the middle because this top part is symmetric. And then I go up 8. Well, we could do the math on that and figure it all out. Okay, if we wanted to do that, the centroid would be equal to, or sorry, I want to do it as y bar would be equal to the area times area 1 times y1 plus area 2 times y2 divided by the sum of the areas, right? Well, that's equal to the beauty of that. The beauty of that is that area 1 is equal to 2 times 10. Area 2 is equal to 2 times 10. So I've got 20 times, what's the height of the centroid of that? Well, it's going to be 5. So I'm skipping all over. My watch is hitting the screen. 20 times 5 plus 20 times, where's the centroid at the top? Well, it's 10 plus the centroid. It's actually 11. And then I got to divide that whole thing by 40. So that, sorry, that's going to be equal to 100 plus 220 equal to 320 divided by 40 is equal to 8. Hey, isn't that what this told us? Cool. Okay. So, as far as my tasks go, I is equal to 533 inches to the 4th. My y bar is equal to 8. So now we got to find q. Well, q is going to be q is equal to y of the height of the centroid of that area times the area. That's if we cheat, and if you go back through the section. Sorry, struggling. Might have to take a break. It's y the centroid times the area of that. So that centroid, now we got to go back to the problem statement. 4 inches above the bottom. All right. Let's go back to our picture up here a sec. That means if I'm worried about it on this plane, which is 4 inches up, right? Then the centroid of this is only 2 inches up, which means it's 6 inches down. So that's, it's 6 inches down times the area, which is 2 inches times 4 inches. So that's equal to 2 times 4 is 8 times 6 is 48. I was going to put inches, but I got to put inches cubed to get my units. And so I've got that. There you go. Let me get rid of that little part there too. All right. So I found I found Q. I know T. I got to find VR. Unfortunately. Well, no. VR is actually pretty easy. Let me paste this picture back in here for you. Or actually for me. If we remember what we're doing, I've got reaction forces here, reaction force here. Because this is all symmetric, I know this is 900 pounds. And this is 900 pounds. Now, I'm jumping ahead because I know this really, really well. You might want to go through the free body diagram to figure this all out. But if you did a sum of the moments is equal to 0 is equal to, and I'm going to sum that around here, around the origin, it's equal to 1800 times 750, and that's in foot-pounds. Sorry, 7.5 foot-pounds. And that's going to cause it actually to go negative. And then plus the force. Oh, I hate that. I think my watch does it. Maybe I can take off the watch. The metal band is hitting. Excuse me a sec while I pop the watch off. The force on the right times 15 feet pounds. And you're going to get the force on the right is equal to 900. I mean, you can just see it coming out of there. It's all fine. Okay. So my shear and moment diagram, my shear diagram looks like this. It starts up 900, drops there, and it comes back. So this is 900. So I know VR is equal to 900 pounds. That was not nearly as bad as I thought. Hold on one sec. I'm going to get a beverage because I'm about to cough again. All right, so my shear is equal to VQ over IT is equal to 900 pounds. Q is, I've got to go back and find all my answers, 48 inches cubed. I was 533 inches to the fourth, and T is equal to just the thickness, so that's 2 inches. You can see my units work out. I've got inches to the third here and inches to the fifth on the bottom, so I'm going to come up with PSI, and then I just got to do the math to get there. It's going to give me 40.5 PSI. Not really a ton, actually, for shear stress. It's actually really, really low. But now, another way to look at that problem would be to go back to, hey, it's a, is it an I-beam? Yeah, let's see what happens if we plug in T is equal to V over A. It's not really an I-beam. It doesn't have top and bottom. But the A, my load would be 900, and my area would be 20, and that's going to give me 45 PSI. Now, you have to make the call. Are those the same or are those different? With that, I'm taking a break again. So, that was part A. Here's part B. The maximum transverse shearing stress. Well, where's the maximum transverse shearing stress going to take place? That's where Q is the largest, and that's on the neutral axis. So Q at that point is going to be 8 inches up from the bottom. So Q goes from, Q is going to be on average, right? That's going to be 4 inches down, and then my area is actually going to be 2 times 8. And so that's going to give me 2 times 8, 16, so times 4, 64 inches cubed. And that's going to substitute right into this one. And so it's going to be a little bit larger, and if we multiply that out, we're going to find that now, not Q. What we're going to find is that the shear is equal to 54 PSI. Now, we had this at 40, we have this at 45. If we go back to our formula, which I didn't even show it. There's our formula. It's the average stress. Oh, sorry, I should have got rid of that. It's the average stress that we're getting. So maybe I should rewrite this average. And it falls in that range. So now, is that worth tracking all the extra? Because it is a bit of extra work to get. I mean, I still had to find T. I had to find my shear V. But okay, let's think about it. Next part. The average shearing stress in the joint between the flange and the stem at the 6 foot. Okay, so what they're asking is, if I go back to that picture, right, I've got this and I've got this, and this is being held together in here with a layer of glue or something. I'll slide that away from my head. That's being held together with a line of glue. And so we need to, we want to evaluate what the shear stress is in that. So this is really just an ongoing exercise of how do we calculate Q? Which, if you go back to our formula sheets, I'm not interested in Q. So at this point, I almost want to walk away from the problem. But we're learning all those things. So let's start pounding that out. Okay, the key for that is we're now taking we're now doing Q for this in a sense. Oh, I got red. I thought I had rainbow colors. And so what's the distance of that centroid? Well, that's now 3. And so for section C, Q is equal to YC is equal to 3 inches times the width is 2 inches and the length is 10 inches. And so now I've got a value of 60. Q is equal to 60. Little bit less than the 64. Well, that makes perfect sense because that centroid is the place where the centroid of area is where I'm going to get the maximum shear stress. So this is going to be less. I don't know that I would have calculated this in reality. I would have said, look, worst case is this. It might be close to this. What kind of glue do I have there? How does it hold up? Well, okay, so just to give you a number, if I use 60 instead of 64, right, then I'm going to come back with 50.6 psi. Again, shear is equal to minus VQ over IT. Actually, and they're dropping the minus. Did I put the minus in by accident? See, I don't use that formula, but that's all right. Let me get rid of that problem. Let me get rid of the problem statement. Sorry, I hope that didn't screw you up too much. So if you want to know, how much force, so there you go. I don't. The force transmitted by the flange to the stem by the glue in a 12-foot length. Well, let's assume D, if VR is equal to a constant equal to 900 pounds, then I always have that. Then shear is equal to 50.6 psi. My area is equal to 2 inches by 144 inches, right? It was a 12-foot long. A 12-inch length, sorry. 12-inch. So I got to get rid of this. 12-inch length equals 24 inches. And so then my force, V, right? Because I really want to use this equation. Shear is equal to V over A. V is equal to 50.6 times 24. Well, 20 times 50 is 1,000. 4 times that, it's about 1,200. If I looked in the if I ran a calculator, I would get 1,251 pounds. But I didn't use a calculator, and I got 1,200. I don't know. Give me credit? Half credit? Partial? My equation's right. Fine. Last part, E, the maximum tensile flexural stress in the beam. You got to learn the language. Those are a lot of words, but they're totally changing direction on us. Tensile flexural stress. They want stress in the x direction minus MC over I. Now I got to go back and find that. That's a whole nother problem. We're not worrying about that. I hope you're doing well. I hope this video has audio. I got other hopes and dreams, but, I hope you're doing well. Don't worry. There's more to come.